In this video, we'll use two quick approaches for doing forecasting using Python and R. I will use Python 1.70 as my IDE, and I will use Prophet, which is a forecasting engine released by Facebook, and the auto.arima function that comes in the forecast package in R. In this example, I will load a manufacturing index from Argentina and forecast it for the next years using Prophet in Python 3.8. I will explain when I think it works well and when I think it doesn't. Then I will show you how to solve the same problem in Prophet but using R. Then I will show you how to have a quick look at a series and see if it looks promising as a forecastable series. It will be a good excuse to show you how we can build a simple anomaly detection system. The idea is to flag abnormal values in a time series, and it is used a lot in the industry. And then we will jump into the famous auto.arima function in R, which is not available in Python. Then I will present an example using auto.arima that won't work very well and confuses every single person learning forecasting. Namely, why do the forecasts look flat? Finally, we will run Prophet on another series, in particular the amount of energy generated by a company in Argentina, and it will look quite well with no serious problem. Before starting, you need to visit this GitHub repo and download the code in here. Then you need to install Python and configure Python and R in there. Also make sure you install all the packages that I will use here. The idea behind forecasting is very simple. Use a series of past values to predict the future. It is, however, a tricky topic in data science, not because there is any lack of techniques, but because certain things can't be forecasted. Imagine how easy things would be if we could forecast stock prices. We will all be rich. Identifying which types of series can be forecasted is kind of an art, where some training is necessary. In essence, most statistical forecasting techniques try to decompose a series into three things: a trend, a seasonal pattern, for example a monthly pattern, and a remainder. Then they attempt to find some stochastic process that explains that remainder. However, not everything in that remainder will be explained. A final residual or noise will remain in there, and that's totally fine. Forecasting techniques using neural networks use a different approach that I won't discuss here. Coming back to my previous point about what things can be forecasted, and connecting to my previous point about how series are decomposed, what are examples of good things that we can predict? Long story short, series that have an inherent structure, such as the number of errors that occur in an IT department, people attending work, retail sales, production numbers, weather, etc. On the other hand, things that can take any value and respond to news are the worst things that we can try to predict. For example, crypto prices, stock prices, sales for small companies that are growing exponentially, and to some extent many things in epidemiology. We could try to forecast number of cases for a particular disease, but if those numbers depend on number of vaccinations or public policy, the behavior of those for the future is largely indeterminate. Prophet has made a big impact in the community because it allows us to deal with very complex seasonal patterns with just 2 lines of code. Here I just load my data. This will be a manufacturing index for Argentina on a monthly level. I need to specify the columns as DS and Y in order to use Prophet. DS will be the time and Y will be the value that I want to forecast. Let's see it here. You can see the values on the left and the plot on the right. Then I do the actual Prophet part. The main thing here is the make_future_dataframe, which is what Prophet will try to predict. I will forecast 36 periods and I need to specify M for monthly. The predict function here actually makes the predictions and they are stored in the forecast data frame here. As you can see, the dots are the actual observations, the blue line is the prediction, and the light blue area is the confidence interval. Note that for the future ones, there are no black dots, as we haven't yet seen those actual values. The plot_components function can be used to see what's inside Prophet's prediction. Check the trend. Can it really be considered a trend? Trends should be almost linear. Anything not linear is probably telling us that there are long-term dynamics there that we're not probably capturing. For example, this trend effect is probably reflecting political factors, commodity prices, or demographical factors impacting Argentina's economy. Going back to the forecasts, the last column Y hat is the number of forecasts that we are after. Bear in mind that it will fall in the middle of both the upper and lower confidence bands. Now it's R's turn. The idea is the same. and then the same logic applies. Let's run everything connected to my starting panel by clicking in here. The results will be propagated downwards. I want to show you a few things that are specific to R and are used very frequently. First, we can call the decompose function to decompose a series very quickly. It shows the trend, the seasonality, and the random component. It's very similar to Prophet, but it's somewhat more concise, not intended for forecasting, and also shows the random part. In consequence, it is just used for analysis. This random part is very useful. It allows us to see if there are any weird outliers, and also if there is any weird structure in there. Let's look in here. There are two warning signs for me. First, there is a huge outlier in 2020 due to COVID. This will corrupt whatever model we build. The other thing that worries me is that the dynamics seem to be very different from 2006 to 2009 compared to the rest. The series moves very violently in those first years, and then, for example, around 2010 it moves very slowly. Time series models can't really handle this very well. Ideally, I would like to see something in here that has the same dynamics across the whole time frame. With this in mind, we can build a basic anomaly detection system. We can just flag values using a box plot. Remember that whatever values are outside the box plot bands are typically considered outliers. We could use these points in an anomaly detection system and flag them appropriately. Anyway, let's assume that we continue with this, and we ignore the trend problem previously mentioned via Prophet. We also ignore the problems caused by these outliers, and we're also ignoring the fact that we have two different dynamics. What we could do here is to use the so-called ARIMA models. You can read more about them elsewhere. Basically, it entails a complicated process of decomposing a series as I did above, in a trend plus a seasonal term plus a random structure, and then finding an appropriate stochastic process that fits into it. Finally, all three components are aggregated to produce a final prediction. But instead of doing that, we can use the famous auto.arima function from the forecast package. It is widely used in the forecasting community. We literally just call auto.arima and it will return the best ARIMA model, literally with one line. Quite impressive. So looking into the coefficients, there is something I don't like. The confidence intervals for the AR parts, the autoregressive parts, include the 0. They go from minus 0.20 to 0.001. That means that the 0 is included in there. In other words, it means that that coefficient is, statistically speaking, considered to be equal to 0. It is non-significative. This shows a problem with the auto-forecasting tools. They don't give us the same flexibility as we would have if we had the manual approach using the full ARIMA process. We should check if these residuals are stationary, meaning, do they have any structure? In this case, the null hypothesis is that they are stationary. Since the p-value is 0.19, we don't reject the null hypothesis. So overall, this auto.arima passes a basic check, obviously with some concerns on the quality of that autoregressive further 1 coefficient, AR1 coefficient. I will now explain something that confuses everyone using ARIMA, namely the flat forecasts. So let's use auto.arima and turn off the seasonal part. That means that auto.arima will search among small models of a maximum of 5 lags, which is the default value for the P and Q parameters that the auto.arima has, and you can check on the documentation. If we had the seasonal part on, auto.arima would be capturing seasonal long-term patterns, for example, correlations of order 12, because we have monthly data, or of order 24, which would correspond to a 2-year correlation. Let's now predict. You see that those forecasts are flat after a few predictions? Check the model. The best model was an ARIMA with actually 2 lags, meaning that after 2 periods the forecasts will look almost flat. The irregularity in the forecasts appear when previous irregular data is used to fit the model that we fitted. But because we can only capture up to 2 lags, that effect disappears quickly. At the end, the prediction converges to the mean of the stochastic process that we just fitted, and the mean is just a constant number. Let me finally show you an ideal example that would look perfect in Prophet. Let's go into Python. In this case, we use a different series. We use the amount of electricity in gigawatts hour that a company produces in Argentina. Python allows us to create linked panels. These contain exactly the same content as the panel used to create them by clicking in here. and won't allow us to modify them. The green dotted line is used to indicate that these are linked. They are amazing for explicitly marking parts of our code that are duplicated. All the changes done to the original panel propagate through the linked one. I will obviously use a different panel with different input data. You see that downward trend? It looks exactly how a trend should look like, not like the trend that I had in the beginning. If I had to rely on this model to make long-term predictions, I would feel certainly much more comfortable than in the previous case.